All right, it's 5:30, so let's go ahead and get started today. Good evening, everyone. How's everyone doing today? Good, good. Yeah, it's week 4 already, so it definitely feels like the beginning of the semester kind of flew by us because like now midterms are going to start happening and then midterm projects are going to start happening, and so we're going to hit the busy part of the semester. So just want to make sure you guys are taking care of yourselves. I know school is really important, but your health and mental health, that's always going to be number one. Okay, and so just a little note for today. I might be struggling a little bit to lecture today because this mask is like really tight on me, and it kind of restricts my breathing. And so in my last class, I was like kind of like struggling to kind of breathe while I'm talking. So if I have to pause just to catch my breath, I apologize, but I'll try to keep it I'll try to keep it good for this. Okay. And so last Wednesday, we did our second ANSYS activity. And so we did our ANSYS activity on a bike crank, okay? So, hopefully you guys enjoyed that one. It's a little bit more advanced than the first one that we did, okay? And so now that we've done a couple ANSYS activities, I think, now is kind of a good time in the semester to actually start talking about some of the details of the things that you've been doing in ANSYS, okay? And so I kind of structured this very intentionally. So I kind of started this kind of after the first 2 ANSYS activities on purpose, so that you kind of have a good idea for what we're going to be talking about over the next couple of weeks. And so today, we're going to be going over meshing, okay? And so I know for meshing, there's been a lot of stuff that we've been doing, and a lot of it is I've just kind of been telling you what to do, right? And so hopefully after today's lecture, like you'll have a better idea of what are all the settings that I'm having you do? What do they all mean? And why am I having you set things a certain way? Okay. And so this is going to cover 3 lectures. We're going to cover kind of the basics of kind of what I think the 3 most important parts of finite elements are, which are the meshing, the boundary conditions, and then the material properties. Okay. And so this week we're going to do meshing and boundary conditions, and then next week we're going to do material properties. And then armed with that knowledge, I think you'll probably have a much more holistic view before our next ANSYS activity, which is going to be next Wednesday. Okay. Okay. So are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get rolling. Yeah. And so the topic for today is what I like to call meshing basics. Okay. All right, so the reason I call this basics is because we'll be talking about meshing a lot more this semester because it's kind of the deepest part of finite element theory. Okay, but I wanted to have kind of just a 1 lecture kind of self-encapsulated lesson just to kind of get you started with meshing. Okay, because there's a lot to meshing that we've never talked about before, and I think it's probably one of the most confusing things to set when you're first learning ANSYS. And so I kind of created this set of lecture notes just to be kind of self-contained and just to kind of get your feet wet of the terminology and what all these things mean and what effects that they all have when you're setting these in your ANSYS simulation. Okay? And so let's start really basics. And so let's kind of redefine what meshing means. Okay. And so meshing basically is the act of taking some kind of complicated geometry. Okay. Okay. And I use the word complicated here, which is kind of a subjective word, but when I say complicated geometry, I mean something that's more complex than a cube. Okay. And so that has more, more complexity than a cube, then you have a complex geometry. Okay. Right. And so meshing means to take any kind of complex geometry and to break it up into a lot of simpler geometries. Okay. Or simpler shapes, I guess you could say, right? And so, just to kind of get a visual picture, right? So let's say that we have this, potato ditto amoeba shaped thing, okay? And so this classifies as a complicated geometry because it's, I don't even know how to define it, right? But it's not a cube or it's not a square. And so if we wanted to mesh this guy, we would take it and just break it up into a bunch of, squares. Okay? And so you guys have seen this, right? And so in all the ANSYS activities so far, we've applied a mesh to our object. And that means that, we just took our geometry and just broke it up into a bunch of shapes. Okay. All right. And so the key to meshing is that, we know exactly what the form of the shape is that we're breaking into. Okay. And so another way to say that is the shapes that we break this thing into are predetermined. Okay. Or in other words, ANSYS, and us too, because we're the operator, we know exactly what kind of shape we're going to break it into, right? And so for the first activity, we broke that 2D plate up into a bunch of squares and sometimes triangles, okay? And then for the bike crank that you guys just did, we broke it up into hexahedrons, which are basically cubes, or we broke it up into tetrahedrons, okay, depending on which settings that you do, okay? But the important thing is that we know exactly what shape it is beforehand. And the reason for that is, we can take those simple shapes and we can solve the governing differential equations on those simple shapes. Okay. And, of course, we're not going to get into the details of how that happens, but, just know that having the shape be predetermined is a necessary step in order to actually solve the equations. Okay. Okay. And so, when you think of producing a mesh on a geometry, there are literally infinite possible ways that you can mesh geometry. Okay. And so there's, it's really hard, and in fact, it's impossible to say that, this mesh is perfect for the situation, right? There's no way to say that there's no perfect mesh. Okay. Okay. But with that said, even though there's no perfect mesh, there are some meshes that are better than other ones. Okay. Especially when you talk about, meshing for finite element simulations. Okay? Okay. And so what we're going to talk about today is, how do we actually characterize what a better mesh looks like, right? And so what are some of the metrics that we use to say that this mesh is better than the other one, okay? And then what you can do is you can use that knowledge to, tinker around with your meshes in ANSYS, right? And so if you know the metrics that you can use to say that, one mesh is better than the other one, then you can, start to move your mesh towards, a really good or perfect mesh for a specific problem. Okay. All right. And so, just like I mentioned before, that meshing is a very, very rich topic. And so, we're going to be spending a lot of time on meshing this semester. But, this set of lecture notes here is just to give you the basics to kind of get started. Okay. Okay. So any questions on this so far? Okay. All right. And so let's start talking about, what makes a good mesh. Okay. And so, to put it simply, a good mesh, a good finite element mesh is one that will produce an accurate finite element simulation with as little computational cost as possible. Okay. And so the reason I underline those two words, accurate and cost, is those are kind of the two kind of main metrics that you can use. Okay. And these two metrics are often antagonistic to each other too. Okay. And so it's, it's good to have a simulation that's accurate. It's also good to have one that's cheap, but these, you can't have both things at the same time most of the time. Okay. But you can find a good balance. Well, let's talk about, what do I, let's kind of expand a bit on those underlying terms. And what do they mean? And how do we achieve those things? Okay, so let's start with accuracy. And so accuracy basically refers to how well your finite element simulation will replicate reality. Okay. Okay. Because we know that our finite element simulations, they're mimicking or they're emulating kind of a real life engineering situation, right? And so you have a real geometry and you're applying real kind of loads and real constraints to them, right? And so an accurate finite element simulation will be one that kind of does the same thing as reality is, right? So it mimics the exact same deformations, it mimics the same structural stresses. Okay. And if you're running a thermal simulation, it mimics the exact same temperatures and heat fluxes, all that stuff. Okay? And so accuracy basically is how well can your simulation mimic it. Okay. And in fact, it's a necessity, right? And so if you want your finite element simulations to be actually useful, then it has to actually have the good representation of the reality. Okay. And so generally, what you can expect is that the smaller your elements are, the more accurate your simulation is going to be. Okay. Okay. Right. Smaller elements means higher accuracy. Okay. And the reason for this is that across each element, what finite elements is doing is it's making an approximation for what it thinks the solution is. Okay. Okay. And so the smaller your elements are, the less approximating it has to do. Okay. And the less approximating it has to do, the more accurate your simulation is going to be. Okay. And so you want to minimize, this approximation as much as possible to kind of, maximize your accuracy. Okay. All right. So on the next page, I'll kind of illustrate, kind of give you a simple 1D illustration for what's happening, when you refine the elements. But for now, are there any questions on any of this? Okay. All right. So let me draw kind of a quick example for you to kind of show you what's going on. Okay. So let's do kind of a 1D example here, okay? And so let's say that we have a function that we want to approximate with FBM, okay? And the function looks something like this. Okay, so we have this kind of parabolic behavior, okay? If we wanted to use just one element to approximate this, okay? And for now, let's assume that it's a linear element, okay? And so what that means is that on that element, it's going to assume that the solution is linear. Okay. On the finite element, it's going to look something like this, right? And so you have just a linear line that goes between the two endpoints. Okay. And so from this, you can see that all of this kind of area in between here, where where the red line deviates from the black line, all of those are inaccuracies. Okay. And so when you only have one element, you're kind of missing all of that detail in the middle. Okay. If you compare this to a case that, let's say that we just increase the number of elements to 3. Okay. Right. And so by increasing the number of elements, we're making them naturally smaller. Okay, so let me draw my function again. Okay. Right. And so if we use 3 elements on this, we're going to have two midpoints here. Okay. And so if we compare the shaded areas for both, which is where the finite element simulation deviates from the real one, when you have 3 elements there, it has to do a lot less approximately. Okay. And so the error is going to be, the error is going to be a lot less than 3 for 3 elements, and the accuracy is going to be much higher. Okay. Okay. Right, and then you can kind of continue this example, and so maybe use 10 elements or 50 elements or 100 elements. Okay. Eventually, you're going to reach a state where the finite element solution is going to basically match that that curve exactly. Right. That's kind of where you want to be to kind of maximize that accuracy. Okay. All right. Okay. And so generally, smaller elements, higher accuracy, right? But element size is not the end all be all for accuracy. Okay. There's a lot of other factors from your mesh that can affect the accuracy. Okay. Okay. And so things like the element shape, the skewness, and the topology of the geometry. So all of these have a big effect. Okay. And so size isn't the only thing that affects accuracy, but it's one of the bigger ones. Okay. I would even go as far to say that size is the biggest contributor for accuracy. Okay. So let's revise this. And so let's say size makes biggest contribution. Or it's the rate limiting step. Okay. Because with the fine mesh, I'll say this. So with the fine mesh, there's still ways that you can mess it up and still get an inaccurate solution. Okay. But it's a lot less likely. And so with a coarse mesh with much bigger elements, it's really hard in order to get that coarse mesh to give you an accurate solution. Okay. And so if you can refine your mesh into a lot of smaller elements, that's going to help you a lot in terms of accuracy. Okay. Because there's just a lot more that you can do with the mesh. Okay. And so that's accuracy. Okay. Right. And it's actually, throughout the first couple activities, I've actually had, quite a number of people ask me, if accuracy, goes up as the size goes down, why don't we just, just put a ton of elements in there? So why don't we just give it just a gajillion elements, and just say that we're gonna have the most accurate finite element simulation in the world, right? And so the thing that kind of stops you from that is the, is the computational cost. Okay. It's like that one meme of, of that guy that like wants to hit on that girl as she's walking past him, and he tries to go for her, and then, the guy that stops him is computational cost. Okay. Okay. And so computational cost. And so as the number of elements in the mesh increases, so does the computational cost. Okay. Okay. And what do I mean by cost? Because cost is kind of a vague term, right? Because you're not actually paying any money for this, right? And so when I talk about cost, I mean things like, how long the simulation is going to take, or time, and also just the amount of memory that your simulation is going to take up on your computer. Okay. Okay. And so you can test this out with your, with your activities so far. So try running the simulation with a small number of elements, so maybe something in the thousands, and then try running your simulation with something, in the 100,000s if you can on these computers. Okay. You'll notice a very big difference on how long you're going to wait for your solution, right? And so when you start to get up to the 100,000s, you're going to start to wait a few minutes for your solution sometimes, depending on how complicated it is. And a lot of times that's not trivial because, for the ones we're doing in this class, you might think, I'll wait 5 seconds for a simulation versus 5 minutes. That's not that big a deal. I'm a patient guy. I can wait 5 minutes. But once you start to get into some really kind of, really complex, professional simulations that run up to like billions of elements, you're talking about the difference between, 5 days versus, maybe a couple of weeks to get your simulation results. And, then it starts to make a big difference. Okay. And so you can't just, just kind of willy-nilly run up your element count, because then it's, it's gonna start taking a lot of time. Okay. But for this class, you don't have to worry about, your simulation taking days, because, we're working with kind of a limited license for ANSYS, and so ANSYS will kind of stop you kind of before it gets too late. Mostly because they want you to buy the professional one, which is, very, very expensive. Okay. Any questions on this? Okay. And so we have these two factors here. And so we have accuracy and we have cost. Okay. And so these two factors kind of work in opposition to each other. Because from an accuracy standpoint, you want to keep adding more elements, right? And so you want to keep adding elements until you, until you reach an accurate solution. But from a cost perspective, you want to reduce the number of elements, because that's, going to be a much more, a quick simulation. Okay. And so kind of the tricky balancing act that you're always performing with your mesh is, you want to have a mesh that's accurate enough. Okay. And so kind of the sweet spot to be in is, is to have a mesh that produces results that are accurate, just barely accurate enough. Okay. Okay. Because if your mesh is just accurate enough, then you kind of put in the exact number of elements that you need in order to get the accuracy that you want, without paying, kind of unnecessary cost. Okay. And, I use kind of the term, just enough here, that's kind of a vague, very non-sciencey term, but, unfortunately, the accuracy that you need for a situation, it depends on what kind of application that you're running, right? Because there's a lot of finite element applications where, maybe you don't need the exact number of the stress down to like the 5th decimal, right? Sometimes you just need to have kind of a general idea of, where the high stresses are in your structure, okay? In those cases, you can kind of get away with, maybe a coarser mesh just for the sake of, of efficiency. Okay. But there's also applications where you really do need to estimate things down to like the 5th or 6th decimal. There you need to really kill it with accuracy. Okay. And so, this is getting a little bit ahead of ourselves, but, later on in the semester, we'll learn a technique called the mesh convergence test. Okay. And so with the mesh convergence test, this is a tool that'll help you determine, what's the perfect amount of elements that you can use for your simulation. Okay. And so basically, what this test looks like is that you run the simulation. With a different number of elements each time. Right? And the goal for a mesh convergence test is that eventually what you should see is that if you're plotting some kind of key result from your simulation, so maybe like the maximum stress, eventually it should plateau. Okay? Okay. And so generally these mesh convergence tests look something like this. Okay. And so on the x-axis here, you have the number of elements. Or another way that you can characterize that is the element size. Okay. And on the y-axis here, you have something like maybe stress. Okay, so some quantity of interest. It doesn't matter all too much what it is. Usually you want to get the result that's hardest to converge. Okay. And then generally what you'll see is that, as you refine the number of elements, or as you refine the mesh, okay, eventually you're going to reach a point where any further refinement of the mesh isn't going to change the result. Okay? And so once you kind of reach this point, so when the graph kind of starts to plateau, okay, once you kind of reach this point, then any further refinement basically won't give you any benefit. Okay? Okay. And so generally, that's the best place that you want to be. And so if you can kind of reach that place, where you can say that, past this point, I can refine the mesh more, but it doesn't really do anything for me, then this is a surefire way to tell you that, my mesh is, the sizing that I chose for this mesh is that's good. Okay. Yeah, question. Yeah, that's a great question. Yes. Yeah, no, that's a good question. So the question, for Zoom people is, how do we run this kind of test without actually running up the cost, right? Because in running this test, you kind of defeat the purpose of finding the perfect mesh to begin with. Because in order to get these data points here on the right, like you have to run like a really expensive simulation in order to get those data points. And so one way that you can kind of do this is that, without kind of getting these data points over here, if you're kind of tracking the trajectory of this curve, and you can see that, once you kind of reach a certain point that it's starting to plateau. And so you can see that the percent difference in your quantity of interest is like maybe like 1% or something like that. Then you can say that, I've reached a good point where, the mesh is good. But actually, the real reason that you run these mesh convergence tests is to kind of show other people that, the mesh that you chose is good. And so a lot of times, when you're making a technical report with finite element results, this is often something that you have to include just to show people that, the mesh that I chose is actually converged. And so it's not something that you do to actually save cost. It's just to show, it's mostly to show people that, my simulations are legit and they actually have accurate results. And so, the reason I'm not really going into too much detail here is that this is actually used as a technique to kind of verify and validate your results. And so we'll talk about it a lot more then. But this is kind of just an illustrative, case just to show that, as you refine your mesh, your solutions will eventually plateau. Yeah. And so I won't ask you to do these yet, but this is something that I'll ask you to do, later on in the semester for the projects and assignments. Okay. Any questions on this? All right, and so that's that's kind of your first metrics on what determines a good mesh. And so now let's talk about element shapes very briefly. And so the element shape, kind of refers to just whatever shape your element is. Okay. And just like I mentioned earlier, is that the key part of finite elements is that the shape that you're going to use for your mesh is kind of predetermined beforehand. Okay, so ANSYS kind of knows exactly what it's looking for. Okay. And so with that said, you only have a very limited selection of shapes that you can choose from. Okay. And that's by design, right? And so, just to, these are kind of the simplest shapes that you can choose to solve differential equations on. But you do have a little bit of options, okay? And so, I kind of group these kind of, into this table right here, okay? And so on the one hand, you can choose what I like to call kind of the triangular elements versus the rectangular. And then there's versions for these in 2D and 3D. Okay? So let me kind of draw the table for you. Right. So on the one hand, you have 2D versus 3D. And then I like to break these down into the triangular element shapes, okay, versus the rectangular shapes. And so under the triangular category for 2D, our triangular shape is a triangle. Okay. So it's a simple, 3-node triangle. And in 3D, the corresponding triangular shape is a tetrahedron. Okay. Okay. And so a tetrahedron is a four-sided pyramid. Okay. And so in 2D, the rectangular shape is it's known as a quadrilateral or quad. In 3D, it's a box or a brick. Okay. And so these are often called hexahedrons. Okay. But sometimes, if you kind of read, forums on finite elements, or you kind of, talk to people, sometimes they'll call these brick elements. Okay. Because they're shaped like bricks. Okay. Also, I think hexahedrons is kind of a long thing to say, so people just like to call it bricks. Okay. And so if you're doing a 3D simulation, your choices are either tetrahedrons or hexahedrons. If you're doing 2D, your choices are triangles or quadrilaterals. Okay. And so what kind of effect do these shapes have on the simulation? And so let's start with the triangular ones. And so the nice thing about triangular elements is that you can use them to mesh any geometry. Okay. Okay. And so if you're using triangular element types, you're never going to get a situation where, where ANSYS says that, I can't mesh this geometry with, with triangles. Okay, because there's a unique property that these guys have called the simplex property, which means that you can use them to fill any space. Okay, and so they're, if you kind of compare, you look at the triangular shapes versus the rectangular ones, the triangular shape's kind of a natural kind of lopsidedness to them, right? And so they're not kind of perfectly they don't have multiple planes of symmetry like the rectangular ones do. And so kind of, unofficially, I call them kind of the lopsided shapes. Okay? And so the fact that they're lopsided means that they can be used to fill any space. The downside to using triangular elements is that, even though they can fill any space, they're not very efficient at doing so. And so if you mesh an entire geometry with, the triangular element types, what you'll find is that your element counts are going to go up. Okay? And so if you contrast that with the rectangular shapes, okay, the rectangular shapes are going to be, much more efficient at filling space. Okay. Okay. And so if you mesh the same geometry once with the triangular elements and once with the rectangular, and you kept the size the same, well, you'll find that the rectangular mesh has a lot less elements than the triangular ones. Okay. The downside to using rectangular ones is that, they won't always work. Okay. And in particular, for geometries that have a lot of curves or have a lot of fine details, those are situations where it's really hard to fit kind of these rectangular shapes into. And you'll get a lot of errors from answers that say I can't mesh this with hexes, or I can't mesh this with quadrilaterals. And so, in those situations, you might have to switch to a tetrahedron just to kind of make sure that you can fill it. Okay. And so generally, if you can, generally it's a lot more desirable to use the rectangular shapes. Okay. Just because they are just a lot more efficient. Okay. And so you're going to get a lot more bang for your buck if you can use rectangular. Okay. And so you're going to end up with a much more accurate simulation at a much lower cost. Okay. But again, a lot of times you're constrained by the geometry itself. And so if you have a complex, curvy geometry, then sometimes you're going to be forced to use the triangular. But generally, if you can swing it, then a rectangular element is going to be a better choice to use. Okay. Any questions on element shapes? Okay. All right. And so those are the options that you have for element shape. And so now let's talk about a consideration called skewness. Okay. And so no matter if you end up choosing a triangular shape or a rectangular shape, those elements kind of have a preferred form that they like to have. Okay. Okay. And so what I mean by that is, let's say that, you have a triangle, okay? There's lots of different ways that you can draw a triangle, right? And so you can have one like this. You can have one that's really kind of thin like that, okay? You can have one with a really kind of, maybe two sides that are really big, okay? You have one just like that, okay? And so there's lots of different forms that, a shape can take. So the shape just kind of defines how many sides and how many vertices you have, okay? But there's certain forms, or there's certain structures that the elements can take that are much more preferred. Okay, and generally, at least for the elements that we went over, they generally like to take shapes like this. Okay, and so what I like to call these are kind of the equilateral formation for these shapes. Okay. And by equilateral, what I mean is that all the sides are approximately the same length, and all of the interior angles are also approximately the same. Okay. Okay. And so ideally, all your elements will kind of look like that. Okay. All right. And so the good news for us is that the measure within ANSYS is actually pretty good. Okay. It's even better than a lot of the research software that I use. So actually, just as an aside, while you guys are still writing this down, I actually had a research student over summer that was working with one of my research softwares, but he ended up actually having to do the mesh in ANSYS just because the ANSYS measure is really good, compared to kind of the open source options that are out there. So, thankfully, you guys are going to be working with the good measure. Okay. And so generally, ANSYS will try to give you as many equilateral elements as possible. Okay. Okay. And so it's not something that you have to go for. It's not something you have to set. So ANSYS is just naturally going to want to do this because they know it's a good thing. Okay. But sometimes, there are some corners of the geometry, or there's some features of the geometry where it's just not possible. Okay. And when you start to get elements that don't have that kind of ideal shape, then that's when we say that these elements are starting to become skewed. Okay. And so some degree of skewness is unavoidable. And so unless you're meshing a perfect cube with a bunch of smaller cubes, okay. And so just by the nature of finite elements, some nature of skewness is going to be inevitable. But generally, what you want is you want to limit the amount of skewness, because the more skewness that you have in your mesh, the worse quality solution that you're going to get. Okay. Okay. So any questions on this? Okay. So some skewness inevitable. But skewness will negatively impact your results. Okay. All right, so how do we measure skewness? Okay. And so thankfully, ANSYS, has a way to kind of measure this automatically for you. The only thing you have to do is you just have to, ask it to compute this. Okay. And so, I should have mentioned this earlier, but this whole concept of skewness, it kind of falls under this category called mesh quality. Okay. Okay. Right. And so when people talk about the quality of your mesh or how high quality your mesh is, what they're talking about is, what do the element shapes actually look like? Okay. And so quality has less to do with, how small your elements are. It more has to do with, what do your actual elements actually look like? Okay. And so if you open up one of your previous projects, you can do that later, and you look at kind of the meshing, option that you have, you'll see that there's kind of in the bottom left, there's a tab called quality. Okay. And so what you can do is you can click on that quality and you can have ANSYS assess, how quality your mesh is. Okay. And there's lots of different metrics that you can use to assess quality. Okay. But I think kind of the easiest one to look at is this skewness. Okay. I actually don't know the exact formula that they use to compute this, but I do know how to interpret it. Okay. And so when you ask ANSYS to assess skewness, it's going to give you a number between 0 and 1. Okay. And so if you have a skewness of 0, okay, what this means is that the elements, this particular element has very little skewness and is thus high quality. Okay. Okay. And then the other extreme is if you have a skewness of 1. Okay. And so if your element has a skewness of 1, this means the element is very skew. Okay. And therefore it's low quality. And so when you ask ANSYS to assess quality, what it's going to do is that it's going to visit every single mesh or every single element in your mesh and then assign it a grade of between 0 and 1 of skewness. So I haven't tried it, but usually when you talk about mesh quality, there's a way that you kind of view kind of a color contour of quality in your mesh. Okay? And so just like you see kind of the deformation field or the stress field within your mesh, you can also view kind of a skewness field. Okay. But generally, the kind of the most useful way to do this is to kind of view kind of the overall statistics. Okay. And so after computing the skewness for every single element in your mesh, ANSYS will give you some of the statistics. So it'll give you the maximum skewness, the minimum skewness in your mesh, as well as the mean. Okay. Okay. And it'll also give you a histogram for telling you approximately how many elements have the associated skewness score. And so on the next page, I'll kind of give you an example of what that looks like, what you can kind of expect, and also, what are some good skewness scores that you should aim for your mesh. Okay. All right. So any questions on just the concept of skewness here? Okay. And so just to kind of give you an example, actually, let me kind of draw you, what certain elements would look like if it was, very little skewness versus one that would be very, very skewed. And so in this example here, this triangle that I have on the left, this is kind of a really good element boy. Okay, so this is going to have a skewness of about 0. Whereas this element here, it has one edge that's really, really short, and then the others are really, really long. So you have this kind of really, really stretched out triangle. Okay. And so this would have a skewness that's much higher. Okay. Okay. And this isn't even the worst that it can get. And so, I'm kind of limited here by the iPad, but I've seen elements where, you have one length that's 100, 500 times longer than than some of the other lengths, and so it can get really, really bad, for some of these skewnesses, just depending on the geometry in your mesh settings. And so when you ask ANSYS to basically assess the skewness for you, it'll give you what the max skewness, okay, what the minimum is, and what the mean is. Okay. Okay. And it'll also give you a histogram. And so it'll basically give you a graph down here. And so it'll say, 0.0 to 0.1, have another bucket from 0.1 to 0.2, okay. Another bucket from 0.2 to 0.3, 0.3, 0.4, and so on. Okay. And what you'll see is that, you'll have this kind of like bar chart like this. Okay. And it'll tell you how many elements of of those particular things that you'll have. All right. Okay, and so this is kind of another one of those things where there's no kind of hard and fast rule for what you should aim for your skewness. A lot of it depends on your type of simulation that you're running, right? But generally, for a finite element simulation on a geometry that's not so crazy, you should try to aim for a mean skewness of about less than 0.25. Okay. That's ideal. That's a really high quality mesh. And then your max skewness should be less than 0.5. Okay. Okay. So these are the metrics that I got from the textbook. But I will say that these are really, really hard to hit, especially for any kind of practical geometry. And especially the max. And so a lot of times you'll find that you'll have one element in your mesh, that one bastard element that's going to have a skewness of like 1, and no matter what you do, it's going to be hard to get rid of it. And so a lot of times you might end up with 1 or 2 elements with the max skewness of 1, and thankfully that's okay. And so as long as you only have just a couple of those elements with really high skewness, they're not going to poison your results all that much, although, of course, it kind of depends on the situation. And then the mean skewness, it's again kind of problem specific. But I will say that if you can get your mean skewness less than 0.25, you did a really, really good job on your mesh. Okay. Okay. And so how do you affect the skewness, right? And so generally, as you refine the mesh, the skewness goes down. Okay. And so that's kind of consistent with what we said earlier, where if you refine your mesh, you make your elements smaller, you make it more accurate. Okay. A big part of that is you just make all of your elements higher quality by making a smaller mesh. Okay. But it's also not a cure-all. And so it's possible to have a really refined mesh, but it's also possible to have a really refined mesh with a lot of bad quality elements. Okay. And so you kind of have to balance it with the shape, as well as where you're applying the refinement and a lot of things. Okay, and so this is a topic that we'll revisit quite a lot this semester, just because getting your skewness down is can be one of the most frustrating things in finite elements. But there's a lot of tools that you can do, and so we'll be revisiting this quite a bit this semester. But I just want to kind of introduce this concept to you. Okay, any questions on this so far?
Where did you say we can locate, once we mesh it and evaluate it, where did you say we can locate this in the ANSYS?
Yeah, and so if you click on mesh, and then in the bottom left corner where you see kind of the statistics for how many elements you have, there's another tab there for quality. And so you would click on quality, and then you can assess it there. We'll go over it in the next activity where I can show you. Yeah. Okay. All right, and so that's skewness and quality. And so let's go over element order next. And so element order, it's one thing that I've been having you guys set this whole time, but maybe a lot of you guys have been wondering, what the heck does that mean? Okay. Okay, and so element order, what this refers to specifically is, it refers to the approximating polynomial that's used within the element. Okay. Because remember, finite elements, you're not finding an exact solution to the differential equations, right? You're finding an approximate one, right? And so a big part of that approximation is that, we're going to assume that across each element, the solution is going to behave either like a linear polynomial or a quadratic one. Okay. Right. And so, and those are our two options. And so, in theory, you can have a lot more options than this. And if you go kind of deep into the finite element theory, they actually, they actually make you do more, which is kind of cruel and unusual. But generally there are two options. Okay? So you can either have a linear polynomial or a quadratic one. Okay? And so for a 1D case, the polynomials look like this. Okay? Okay, so for a 1D case, let's say that we have our linear function. Okay, and so the most generic linear function has a constant term as well as a linear term. Okay, versus a quadratic one, which has three unknowns. You have a0, the constant term, plus a1x plus a2x squared. Okay. And this is quadratic. Okay. And so by choosing the order, basically what you're choosing is that inside your element, this is what the solution is going to look like. Okay. And so you're either choosing to make it look like a linear function, or you're choosing it to make it look like a quadratic. Okay. Okay. And so remember, when you're doing a finite element simulation, the way that finite element solves these complex differential equations is that it assumes that, on this element, we're going to assume that the solution looks like either a quadratic function or a linear function. Okay? And so finite elements is going to assume that your solution looks like either one of those things, and then it finds the best possible linear function or the best possible quadratic function, that matches the solution as closely as possible. Okay. And so, normally when you're solving differential equations, you normally do the reverse, right? And so a lot of times you're going to solve the differential equation first. And then from there, you say, okay, I have a quadratic function, I have a cubic function, okay? And so finite elements does it kind of reversely. And so it says that, I'm going to assume that this looks like a quadratic, and then I'm going to find the best quadratic that fits it. Okay? Right, and so your choice of which function to use will kind of affect the accuracy of your simulation. Okay. Because generally, a linear approximation here, just because we have less constants here, a linear function will be cheaper. Okay. Okay. But not as accurate. Okay. So hopefully you're seeing kind of the general theme that, you can't have cost and accuracy at the same time. Okay. Yeah, the term that's often used, or the phrase that's often used among finite element nerds is that there's no free lunch. Okay. And so you can't have accuracy, which is your lunch, for free. And so you have to kind of pay for it, unfortunately. Okay. And so for a quadratic function, this is going to be more expensive because you have more unknowns. Okay. And so you have to pay more, but then you kind of get more benefit from this. Okay. And so I'll do kind of a quick 1D example to kind of show you kind of the differences between these two. Okay. But before I do that, are there any questions on this? Okay. All right. And so let's do kind of a similar graph that we did earlier. Okay. And so let's say that we have a finite elements, or let's say we have a true solution that looks like this. Okay. And so in black here, I have the true solution. And on one side, I'm gonna draw what the linear finite element approximation looks like. And on the other side, I'm gonna draw the quadratic one. Okay. And so for a linear one, basically we're just gonna connect the dots with a linear line just like that. Okay. Because the thing with the linear line is that it's impossible to have any curvature. Okay. Whereas a quadratic one, maybe looks something like this. Okay. And so the thing with quadratic approximations is that you can have some curvature to your solution. Okay. It's not a lot of curvature because it's just a quadratic function. Okay. Because you can have more extreme curvature if you include the cubic term and the fourth order term and so on and so forth. But just being able to have some curvature is a big improvement over linear. Okay. All right. And so, for both of the activities I've given you so far, I've basically told you that you need to use quadratic. Okay. And there's a very specific reason for that. Okay. Because both of the activities we've done so far are structural simulations. Okay. And so it's generally advisable to only use quadratic elements for structural simulations. The reason for that is that, when you do a structural simulation, you have to compute things like the stress and the strain within the elements, and that's a big part of the equations. Okay. And the way that we compute strain, if you kind of remember from our review of mechanics, is that it's computed as the derivative of the deformation, okay, or derivative of the displacement. And so the key here is derivative, okay? Right. And so, I want you guys to think about, what happens when you take the derivative of a linear function versus when you take the derivative of a quadratic one, okay? And so when you take a derivative of a linear function, okay, and so when you take the derivative, okay, and so we look at this function back here on the other page, right? If we take the derivative of that with respect to x, what do we get? And so we see that the a0 cancels out because we take the derivative of a constant. And we see that this x right here goes away. And then all we're left with is a1, right? And so the derivative of a linear function is always going to be constant. Versus a quadratic one. Okay. You take the derivative, and what you end up with is a linear function, right? Okay. And so this actually ends up being really problematic, okay? Because when you're doing structural simulations and you have to compute stress and strain, when you compute the derivative of the displacement field, you end up with a constant strain or constant stress within your elements, okay? And that causes a lot of problems because if you have your entire element under a constant state of stress or a constant state of strain, or in other words, you don't have any spatial variation of stress or strain, then what can happen is that your elements can actually lock up, right? Because when you have an elastic solid or a deformable solid, your solid kind of relies on kind of a difference in stress and strain in order for it to deform, right? And you kind of get this kind of vicious cycle where you want to compute stress and strain, but it's constant on the element, but then that thing drives the displacements, and so you kind of enter this cycle where the elements tend to lock up, okay? And so there's a phenomenon that happens when you use a linear element type for a structural simulation, and that's called shear locking. Okay. And so what can happen in shear locking is that if shear locking occurs, then what you're going to get from your structural simulation is that your deformations or your displacements are going to be much lower than what they actually is, okay? And so if you use quadratic elements where you can actually have, a variation of stress within your element, then that shear locking goes away, okay? And so some of you might have experienced this. And so if you try to do either, one of the previous two activities with a linear element, in particular, one of the linear triangular ones, ANSYS will actually give you a warning that said, it's not advisable to use linear elements for a static structural simulation, right? And the main reason for that is because of the shear locking, where you get a constant stress state within your elements, which is not good. Okay. All right. Any questions on this? Okay. All right. And so we have 5 more minutes, and so there's kind of one more concept that I want to go over, but I think we'll probably finish it more next time. Actually, it's not that hard. Okay. And so that's the concept of mixed meshing. All right. And so we've talked about all these aspects of the mesh, so things like size, things like the shape, things like the order. Okay. And of course you want all these things to be good for every part of your mesh. Okay. But a lot of times, especially when you're working with a kind of a more complex geometry, you might have multiple different parts or multiple different regions to your geometry. Okay. Okay. And these different regions and different parts, they might vary in size and shape, quite a bit. Okay. Or more importantly, one thing you'll see often is that these different areas or these different regions, they might vary in importance, okay? And what I mean by that is, a lot of times you're running a finite element simulation to find out, what's the stress in just one particular region, or maybe you're only interested in the solution in just one region, okay? The rest of the model, it kind of has to be there just to make it easier to apply boundary conditions, but for most cases, you don't give a crap what's happening in the other parts. You only care about just this one region. Okay? And so in these situations, you can actually apply different meshing settings to different parts of your geometry. And so you're not limited to, applying just a size for everything, or maybe a shape for everything, or an order for everything. Okay. You can actually, specify different regions. Say, I want more refinement here, or I want a smaller size here, or I want a different shape here. Okay. And actually, ANSYS makes it really easy to do this. Okay. And so all you have to do is basically just point at an object and just click it and select it, and you can specify different settings for this. Okay. Right. And the way that we do this in ANSYS, and you've been doing this already, and some of you have actually asked me, why are we doing it this way when there's an easier way to kind of do this from the global settings? Okay. But what you can assign things like, you can assign like a meshing object or a sizing object, okay? Or yeah, method object. Because actually, I know I've been making you guys do this for for the meshes so far, but for both the plate and for the bike crank, they're kind of a waste of effort because because we're applying the same settings for the entire mesh, you could actually apply those settings just from the mesh defaults, just from the mesh settings right there. And so there's actually no need to create like a separate method object or a sizing object. Okay? But the reason I had you guys go through that is to kind of prepare you to say that, if you have a model with kind of very complex regions, you can, define different methods or different sizings for each of those different regions. Okay. And it's very simple because, you've kind of done it already. Okay. And so just know that this option is available to you. And so you're not kind of stuck using a meshing setting for the entire thing. You can just kind of pick different regions and, applying a different sizing here, different method there. Okay. And oftentimes that's going to be what's necessary in order to make sure that your mesh can, finish in a reasonable amount of time, or more importantly, you can kind of concentrate the mesh density in kind of just a specific area, just to make sure that you get an accurate solution in this one key area, whereas maybe you don't really care about other stuff. Okay. All right. Any final questions on this before we wrap up for today? Okay, all right. So that's the basics of meshing, and so we'll be revisiting it a lot more. But hopefully, this makes a lot of things make a lot more sense from your ANSYS activities. Okay? All right, and so on Wednesday, we'll cover a set of lecture notes on boundary conditions. Okay, and then next week we'll do material properties. Okay. All right. So thank you guys for tuning in today. Hope you guys enjoy the rest of your evening, and I'll see you guys on Wednesday. Thanks, guys. Okay, so for those of you here, if you want to continue working on your projects here, I'm fine with that, but but you guys know my policy. Just make sure that if you're the last one here, just turn off the lights and shut the door. So, yeah, I'm available right now. What's up? Let me clean up a bit and then I'll come back there. Sure. Wait a second.
Why the linear method is cheap
Yes.
and quadratic is expensive?
Yes.
Why?
Just because per element, for the quadratic method, you actually end up with more vertices.
Oh, yeah.
So I didn't really draw it, but like it's a triangle.
It's getting worse, man.
If you have a
Yeah, I'm
linear
trying to
triangle,
get,
the
I'm
only
trying to get
vertices
these
that you
down for
have are
quick
at the
tomorrow. I
corners.
was having trouble.
And then finite elements, you're gonna be, basically, you're
Honestly,
gonna be
most of
computing
this-
the solution of all of
Everything
it.
else was fine.
But
That
for a quadratic triangle, you actually
and the
add
Z
additional
transform
nodes right here.
I don't know.
And
I
so
don't know
it's,
how
there's
to
just
do
kind of
this
more
series.
nodes that you have to solve.
With
for.
you,
The solutions aren't very helpful. It's just
No,
the answer.
like, yeah, some of them I'm like, oh, I actually wanted to know this one.
Cheaper, you mean?
But
Same
yeah,
about the price, right?
Exactly. And so actually,
Yeah,
you know,
when
you
she
can
started
compare
getting
if
into
you
all
run
like
math,
the
you're
drawing
on elements.
conical and like really.
You know, check the number, don't check the number of elements, but check the number of nodes.
It's getting wild pretty
And then
fast.
run the same math with
But
quadratic.
yeah,
and
man, I was
see
trying to
the
prepare
number of
myself for that quiz tomorrow because I
The
didn't.
amount of elements, which is
I got
basically
maybe
the
like
same,
a little
but
more
the
than half
amount
of this
the
one.
amount of
But
nodes will jump off.
Thanks, yeah,
like, yeah,
So one
we
end
were asked, all
then
asking a
we
bunch
had
of
an
questions.
ordinary
I'm
to
like,
be controlled.
I'm asking you a
Exactly.
question. but I'm not
It'll
really
be the
typing.
same number, it'll be the same number of elements.
So yeah,
just
we'll
each
see. And I'm
element will
already
have
like
one
haven't
node.
even started the second homework assignment yet. So
So the
like,
nodes
a
are
problem
kind of
a
where
day,
you're
but it's
solving
like
the
this
solution.
is
So,
a project.
you know, when
It's like
you solve the finite element solution, you actually compute.
Okay,
things like
man, I'm
what's the
gonna
displacement
symposium.
all right, man. Yeah, I'll see you
here,
tomorrow.
here, 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 here. And so the more nodes that you have, the longer it's gonna take to run, just because there's more nodes to solve.
It will run like node to node.
Exactly.
Thank you.
Mhm.
Bye-bye.
Right? Mhm. Yeah, sure, what's up?
So for the bike activity, the last one, I can't really see the full point on the bars.
It's also pointing down, yeah.
And then. For the capacitor, is it just for the X and Y?
Yes, and so for the, I think for the activity, we had the force meter negative Y or positive Y. And so for compressive, I want you to point a negative X direction. Mhm. Yeah. Yeah, and so I want you to point into the. Basically, the only thing I want to show you is that you can do it like that, then it can be sustain a higher level. I just needed a different loading.
So I thought you meant it was like when it slows like this.
Oh, I meant the entire thing. Yeah. And have it point.
So I guess my question was, okay, so we have normal stress. And I understand normal stress. Right, so then we have the equivalent stress. And I know this is that much more complicated quadratic equation.
Yeah.
So why isn't that the normal stress also doesn't tell me that there's an ion yes.
It is. So if you look at the blue here, you can see that it's almost the same. Oh, it's negative. It's negative.
Oh.
And so negative means compressive. Yeah.
Okay, I just didn't, wait, well, okay, that's,
Yeah,
you know what, actually, maybe it told me something different on the student version.
You might have been looking
I
at
don't remember seeing, this negative value down there. I think it might be something different on the student version, or maybe I just wasn't paying attention because yeah, that totally makes sense that the negative is. Okay. I just thought that made sense.
Yeah, it's confusing because like when you look at the blue, you like naturally you think of like blue means zero.
Yeah.
But sometimes when you look at some blue is just the most. You have to look at control.
And I mean, they are relatively the same. I guess not relatively. I guess, you know,
They're basically the same.
29 is 29.
That's pretty insignificant. So,
I mean, it's basically the same, but what could I say? The line is slightly more accurate because it takes into account.
yeah, so the difference you're seeing is probably from shear. Okay, because that's the thing that the normal stress is not. And so this extra 29 or whatever, you get very little shear in this configuration. Totally different. And so there's very little shearing.
Oh yeah, and then So like in my write-up and also in the last question, we don't really talk about like what we're doing with the light. So I just basically said like in my write-up, like, okay, my answer is gonna change the thing, like we're using the light. I said if it was road, BMX, anything like that, or we're jumping, sprinting, climbing. I should be better probably. If we're just cruising, or if it's a kid.
Okay.
So.
Yeah.
So,
We thought about it a lot more than that. So, but you're absolutely right. It definitely depends on the application. Yeah, I think that's a great answer.
yeah, because I can see like a lot of pro athletes just like pushing this to fail.
Oh, yeah.
Especially like, you know, if you're jumping off something high, because you're landing with much more than your body, right?
Right.
So like, you know, you got a 150-pound rider on there dropping like 6-10 feet. And, you know, that's however much. So, like, let's say 2 meters or something. Yeah, 2 times 10. So it's a lot of force opposed.
Yeah, no, I think that's a great.
And then should I also put in my write-up, like, oh, I put the force going down on the end because I thought that would be.
Yeah.
That would be the highest stress location because, you know.
Oh, yes. Yeah, that's the thing that I want you to talk about in the report. So basically justifying, and we'll talk about this, as we go through this month. Every time you make a setting for that, that's like a conscious decision that you're making for. And you have to be able to kind of justify those. So when you're thinking about, the reason I put this force here, this, that's a great mindset. If you're going to use finite elements, professionally, that's what everyone's going to question. So you give them a finite element results. Why did you choose this force? Why did you choose here? Why did you choose that? If you're prepared to answer those questions, then you have a leg up on. I see a lot of novice finite elements. They say a lot of novice finite element engineers. They ask them, why did you match up this? I don't know. That's all. That's not a sense.
Okay, so I just, like, when you said talk about your mesh, I just like said, okay, this is my mesh, this is why I did it that way.
Exactly.
But I should talk also about the force and my fixed.
Yes. Yeah.
Okay.
So the three things that we're going to cover with the next 3 lectures: meshing, boundary conditions, and topology. We should be able to justify those, whatever kind of report.
I'll go ahead and add that to my current version. I think that's it.
Cool.
All right, thanks, Professor.
Yeah.
Appreciate it. Have a question.
Yeah.
So when you're selecting an element for that.
Yeah.
I found that different. Get the dropping once here, plug that in,
Mhm.
and then mesh itself, and then we specify the method that will put down.
Yeah, so that's what we were talking about at the end of the mix method. So if you specify from this mesh right there, that's going to apply for the entire mesh. But if you do it for this one, it's only going to specify for whatever you select. For here, it's a little bit redundant because we select the entire thing anyway. But starting next activity, we're going to start working on objects that are sensitive. So you can apply a different method or different size. For this one, actually, you don't even use to, because you can do everything you do from the mesh setting. But I'm just showing you that it is an option, and then you can select it.
And then I have a question on the. Kind of hard to see, but I just wanted to verify it's like the fix the part is kind of the application. So when I do this, I pick my fix the board on like this thing.
Yep.
At the bottom as well.
So one of these is the handle. So you can kind of zoom out, and so you're going to fix it on the bottom, which is handle. And so if you it's kind of a weird frame, but it's kind of one that I found, one of the only ones that I found that actually works. And so the pedals is going to be right here. And so actually, I think this top one right here, this is you should apply a force right here. So this is where the 15 comes.
Right, that's very heavy.
Exactly. So that's one down. And you would fix it on kind of the bottom. And then you would also fix it over here. So kind of the interior where the wheels.
Yeah.
That's the other part.
So when you apply for including more instruments.
Yes, yeah, kind of the lip.
Okay. Alright. Thank you.
Yeah. mhm.
A quick question.
Sure.
Not regarding this one.
Mhm.
When I remote in when I'm doing my projects at home, and like when I work here, obviously when I start my project here, I usually have to start over when I remote it, I guess, make the model and stuff because I can't load anything from the remote laptop. Is there any way around that, or am I just gonna have to do it?
So the way that you get around that is if you can open up Workbench real quick, I'll show you kind of the way you do that. This is something I just learned recently too. actually.
Okay, yeah, I thought it was just being done.
Yeah,
I
because
can't
there's
save my work.
yeah, because when you save it, it kind of saves multiple. And I don't know why they do this. It's really inconvenient, honestly. But there's a way that you can kind of zip everything together into a single folder or a single file. And if you transfer that file, you kind of have to email it to yourself. And so when you remote in, you have to email.
Okay, so it's kind of like a pack and go for like SolidWorks.
Exactly.
Okay.
Exactly. Yeah.
Yeah, that would definitely help. I mean, at the time, it doesn't seem too hard to be like, okay, I'll just open up the geometry, mesh it again and all that, but I'm going to the project, I'm like, okay, I have to go and redo all
For these
this.
first two activities, I think it's not that big a deal because
Yeah.
they're simple, but later on, you definitely don't want to start over.
Yeah,
All right, and so let's say that you did your project,
Sure.
build it up, so you go to file, and then you want to click on archive.
okay,
And so what archive, well, right now I don't think is going to work because you don't have.
I don't
it.
have anything there.
But what archive does is that it will take all your geometry, your mesh, and your simulation results, and pack it into like a single zipped folder. And then if you transfer that zip folder, from the remote to your home,
Okay,
you save it on a flash drive or you email it to.
okay, so it'll zip all the data here and even what I
Exactly.
do in the model and everything.
Exactly, yeah,
And then I can just pop that open. And done.
exactly. But then the way that you open is that you go to file,
Uh-huh.
and then you go to import. And then when you import, then you select the zip folder.
Okay.
It'll
So-
take a little bit of time because it kind of has to unzip everything.
Sure,
But it's a lot easier because if you try to save normally, it'll save like multiple files and. like,
right,
a
I was trying
folder.
that, and I was like, I don't know.
But it
what's
doesn't
going
really, but it's not that convenient because it's looking for kind of an exact file location for certain files.
on. Uh-huh.
And if you're kind of moving it between computers, then all those paths get messed up.
Okay,
and
so
so-
this will just zip it then.
That'll zip it and it'll remake all the paths, from it. So this is kind of the way to go. You're kind of working
Okay.
between those.
Okay, if it works just like a pack and go, then I shouldn't have a problem.
Yeah, yeah.
Okay, perfect, thank you.
Yep. mhm. Yeah. The files don't exist or something like that. Oh. Oh, there's some there. I always thought that they were kind of compatible. So I'm guessing you're using R2, 2021 R2 on the. I always thought that those are future. The ones here are 2021 R1. Yeah, the student version that's out there right now could be R2.
Yeah.
Okay. Yeah, you might probably the easiest thing would be to uninstall that one. They probably have R1 somewhere on their website, and I would download that. It's probably if you start the project here, you can probably open it in R2, but I don't think probably you can't open it start in R2. Yeah, and it's all.
Yeah, it's
Yeah, I think that's probably